Hi guys, my name is Kevin. I am the education chair for SCRO. Now, today we'll be talking about the basics of semiconductors, and we would be going into in-depth details of each topic separately. And so today would be like a really basic idea. I'll give you a really basic idea of actually what's going on. It would be like a build-up to what's to come, so you don't need to be scared or anything. Like we would go as basic as possible, and we know that there are a lot of you among you are undergrads, then some graduate students, and you know that each of you have different levels of understanding regarding semiconductors. So we will be starting from the very basic, like zero level. And so let's start. I hope you can all see my screen.
Yep,
Yeah,
we can.
All right, okay. So okay, the first lecture for the SCRO lecture series would be Introduction to Semiconductors. Now, the aim of this lecture would be to act as a starting point for all members. Now, our lectures will be diving deep into real industry applications. So it's really important to fully understand the basic principles. That is, the first few lectures would kind of tell you what's to come and how to tackle the problems that you have towards your understanding in semiconductors and its application in industry. Now, basically, every lecture or every presentation would have 4 questions. That is what, why, when, and how. Now, the whys are kind of tricky because those are usually, especially in the field of semiconductors, those are really research areas, then graduate courses, or some of these are really tricky to understand. So as engineers, what we really need to understand is the hows, whens, and, you know, so the hows kind of explains us when to use semiconductors or how they work, so that how we can use them in engineering principles. Now, for this lecture, the learning outcomes would be understanding what a semiconductor device is, what is Moore's law and its consequences, what is N-type, P-type semiconductor, simplified voltage current relationships, basic device physics, and all the things that you need to know about these things. Now, these are kind of the basics. So yeah, if you know all these things, it's really good, but you might surprise yourself when you see a lecture that there might be a lot of things that you thought you knew, but actually you didn't, or some of things you have doubt about. So we try to clear them out. It's fine because we're starting from zero. All right. First of all, what's Moore's law? Now, Moore's law is the observation that the number of transistors in an IC doubles every 2 years. All right, it was founded by Gordon Moore. He was a co-founder, CEO of Intel, so he's a big shot. Now, in 1965, when he saw the growth of semiconductors, he thought that in the next 10 years, every year, the amount of transistors on a chip would double. And he was right in thinking so. After 10 years, then he thought, all right, a slight change might meet it. So he made it that in every 2 years, there would be an increase of twice the number of semiconductors on a chip, transistors on a chip. Now, it's not any physics or theoretical definition or any science concept, but it's kind of like an observation or statistical prediction by him. It is pretty much simple, like it sees you as having a 2 raised to n. So every year into 2, and it goes. So right now, you can see the graph, and it by when it was 2019, it kind of reached between about 19, it's like a lot of zeros. So it actually held true for more than 50 years. And in the anniversary of his 50th anniversary of Moore's law, we found ourselves in a little bit of a tricky situation. So this is kind of how the Moore's law went on in a practical perspective, like the different chips and the number of transistor count per the chip. So right now we reached, it started with Intel, then came AMD, then a lot of amazing CPUs and GPUs were developed with amazing transistor count density. And this is the kind of, so it shows this distribution kind of is a log distribution. So it kind of shows you how fast the chip is growing. And it's just a kind of an indication of what to come in the future and what to expect for the technological growth in this field. But in recent years, it became increasingly hard to kind of pack more and more transistors into a chip. So the Moore's law curve kind of started to flatten out. So companies are kind of in a pinch to develop techniques to make this thing a reality. So people say that Moore's law is dead, but I would say it's a little bit lagging. So the timeline is getting a bigger and bigger, more than 2 years to double the number of transistors. Right now, you could see the zeros and you can see how much number of transistors are on the chip. So it becomes really, really hard to pack more on a chip. So we can see, we can wait and see what the future holds, but the companies are really developing some really promising techniques. So I hope this technique or trend goes on for a long time. Now, the most important question, what is a semiconductor? For that, materials can be divided into 3 categories, as you all know: a conductor, an insulator, and a semiconductor. Now, a conductor has a lot of charge carriers, which are like electrons. Now, if it can, it's like a pipe that carries water. It doesn't have any very less resistance, and it can flow uninterrupted with a potential difference across the conductor. But an insulator, it's kind of like it acts like a plug in between the pipes. So it's really hard for the water to flow or the current to flow in an insulator. So as it becomes harder and harder, the insulator, this has something to do with the band diagram that I've shown you here. It's showing that basically electrons or atoms have valence band and a conduction band. So the gap between these 2 bands is called the band gap. Now, the higher the band gap, the more difficult it will be for electrons to flow. That's the basic idea. In metals, this band gap kind of doesn't exist. So that's why current can flow really easily. But in insulators, it's kind of like a really big gap. Now, in a semiconductor, it's kind of like a switch, or you can kind of like a tap. I mean, the electrons can flow or not, or can't flow. I mean, there is a certain amount of resistance. The band gap is intermediate between that of a conductor and an insulator. And semiconductors are also denoted as N-type and P-type. We'll get that into a little bit. And there is an important concept called Fermi level, which kind of shows you a level where you can expect there's a 50% chance there would be an electron between these bands. Now, we will get into that in detail. So now the resistance, you can see the bottom, that aluminum, a metal, has 2.7. Then silicon dioxide, which is an insulator, has 10 to the 20. That's a huge amount of resistance. Now, silicon, kind of in the middle of this, smack in the middle, like 10 raised to 10. So you get the idea, right? Now, semiconductors are divided into 2 categories based on a technique called doping. Now, they're called intrinsic and extrinsic semiconductors. Now, an intrinsic semiconductor, it's like a pure silicon. So pure crystalline structure. It doesn't have any impurities, and the number of electrons equal to number of holes, which I will get into a bit. Now, it has a very low electrical conductivity, and the electrical conductivity is temperature dependent. Extrinsic semiconductor is a pure semiconductor material to which an impurity atom is added. The dopants that I previously mentioned, N and P type dopants, are added to the intrinsic semiconductor to make it an extrinsic semiconductor. Now, depending on the amount of doping, the free electrons might not be equal to the number of holes. So an N-type semiconductor has a large amount of electrons, while a P-type has a large number of holes. Now, it has a higher electrical conductivity than an intrinsic semiconductor. As you can see, depending on the number of charge carriers. More charge carriers means more conductivity, right? Now, the intrinsic and extrinsic, the main difference is that both of these are, the intrinsic semiconductor is temperature dependent, while the extrinsic one is temperature dependent and dopant dependent. I mean, the conductivity and every other factor of an extrinsic semiconductor is depending on the number of dopants too. In the right side, I hope it's right for you, or in the left side, the conductivity equation is basic conductivity equation. It's conductivity is the ease for electrons or current to flow. That's the conductivity sigma. Now, in an intrinsic semiconductor, sigma is equal to the product of number of charge carriers, which is Q, and the charge of the charge carriers, which is Q, which is like the unit charge of an electron. Then there is mu E, that is the mobility of either the electron or the hole. Now, as an intrinsic semiconductor has equal number of electrons and holes, the conductivity equation, the electrons and holes kind of contribute to the current. So the conductivity equation has two components, that is the electron component and the hole component. Now, the electron component, the number of carriers is the electron number, and in the hole part of it, it's the number of holes present in the semiconductor. Now, for us, if the semiconductor is a p-type, it would mean that the number of holes is very large compared to the number of electrons, and meaning the number of electrons would contribute very little compared to the number of holes. So we can actually approximate and kind of put the NQ mu E equal to 0. And so that would be the conductivity. Now, what is a mobility? We have been talking about it a bit before. So a mobility is kind of like if you apply a potential, or a field across a semiconductor, how easy is for the electrons to move across. So this is a table for the common semiconductors. For silicon, mobility of N, that is electrons, is 1400. For holes, it's 470, and germanium and so on. It goes up high. So this is at room temperature. Now that's really important. Now you see the curve down below. It's kind of like a temperature and electron concentration for a semiconductor. Now imagine we take silicon, right? This is for silicon, the curve is for silicon. Now, the number of charge carriers kind of increases at 0 Kelvin to about 100 Kelvin and 200 Kelvin, and it is during the range from 100 to about 500 Kelvin, kind of like a flat lines, right? So that is really important because it is within this range that our room temperature, which is about 298 Kelvin, stands. That is really important because this is the range that semiconductors actually operate. That is why silicon is really important for us, because silicon is really good at operating at room temperatures and has a good electron concentration at room temperature. But germanium, gallium arsenide, those things kind of has the same concentration at only a higher or only at a high elevated temperature. So silicon, one of the major advantages of using silicon as a semiconducting or a transistor material is because it's stable and has electron concentration at room temperature. Now, all right, now we get to the dopants part, right? I told you we have N-type and P-type dopants. Now, as I told you, the band gap is, we have a conduction band and a valence band. We know that all metals or non-metals or any atom has valence electrons. It's the most outermost electrons. Those electrons kind of fill the valence band. And the conduction band is typically empty, but once you have sufficient energy from, or thermal energy or any kind of energy at a certain temperature, the electrons or charge carriers from the valence band kind of jump into conduction band. And now as the conduction band is kind of empty, it's kind of like a freeway where cars can go at a really fast pace without any interruption or traffic. So it can go fast, smoothly. So that is why this band structure is kind of important. There is a little more theory to it, but that's beyond our scope anyway. Now, what dopants does is, right? When we add a dopant, like an N-type dopant, for example, an N-type dopant would be phosphorus in this case. Phosphorus has 5 electrons, while silicon has 4. Now, you see this, this part shows the the atoms in the structure of silicon. Now, each silicon would be bonded to 4 different silicon atoms, and it would be sharing 2 electrons. Imagine we are adding a pentavalent, like a 5 element like phosphorus, which has 5 electrons. It would mean that even after joining with all the other silicon atoms, there would be an electron left over. So this electron is kind of like a lone, he feels lonely, so he's also playful. He can jump around from a phosphorus to phosphorus, or wherever there is a vacancy, he can move. Basically, it adds more electrons to an existing semiconductor device. Once that happens, you know what happens when a lot of electrons are suddenly added to it, its conductivity increases. Basically, as the amount of electrons increase, more amount of electrons are available for causing current in the semiconductor. So it's easier for, thus it has a large current capacity. Now, this N, it's the number of donors per centimeter cube. Now, in an N-type semiconductor, the elements we add are called donors because they have an electron and they can donate the electron. So basically, they're called donors, pretty much straightforward. Now, so that's it about N-type. Now, the P-type, it's kind of reverse. In P-type, what happens is we add an element which has, silicon has 4 electrons, but we add an element like germanium, which kind of only has 3 electrons, which means one of its positions is kind of like free. I mean, that position is empty, but it still can hold an electron. So it means that it kind of like acts like a hole where it can take in an electron. So they are called acceptors. Now, imagine that in the structure, we have silicon atoms and like germanium atom. Now, germanium atom kind of has this part where the electron is not present, meaning if there are additional electrons in the system, the electrons can kind of, if they are free, they can kind of move to this part. And from there, if there is another hole, it can move to that part and thus cause current. It's a little counterintuitive than the donors, but they are called acceptors because they create a place or a hole which can accept electrons, right? Now, depending on these things, the Fermi level, which I kind of mentioned previously, changes. In a normal intrinsic semiconductor, the Fermi level is kind of in the middle of the band gap. But as we add an N-type semiconductor, basically it means that there are more donors, meaning more electrons are present towards the conduction band. Now, that means the Fermi level kind of shifts towards the top. Now, Fermi level, as I told you, is a place where you can find an electron easily, like 50% probability, but that's all statistics. We don't need it here. Now, but in a P-type, the Fermi level kind of shifts towards the bottom middle part. So meaning that's where the acceptors are, and that's where more electrons have a probability of being. So that's about the shifting of Fermi level. These are like really basic concepts. You don't need to go into details about it for understanding what is going on. All right, so as we have discussed dopants, now how does dopants translate to electrical properties? As I told you like before, higher dopant concentration means more carriers. N-type means electrons, N-type means electrons, and P-type means holes. So we can denote holes with a plus sign and electrons the minus sign, just for convenience, because holes kind of accept and electrons kind of negative. Yes, so holes are kind of thought of as a positive charge. Now, higher conductivity leads to a lower resistivity because more means there is little resistance for electrons because there are more electrons or holes. It's easier for them to move, so there is lower resistivity. Now, an N-type silicon has lower resistivity than P-type as the same dopant concentration. Now, why do you think that is? Because it's, see, a donor kind of accepts an electron. It's kind of taking electron from another place and taking it for himself, while a donor kind of gives electron and acceptor kind of takes electron. Now, the electron that an acceptor takes is present in the system, while a donor, which has an electron, is giving to the system. So that's kind of an intuitive idea of how the N-type gives lower resistivity than a P-type. So that's it, but that's not it. There is a little more. Now, how do dopants translate to electronic properties? This is a picture of an N-type and a P-type semiconductor, silicon for our case. Now, think of it like this. When you apply an voltage, that is V, across the terminals of it, and there is a current going on, right? So this is a basic equation of resistivity and how it works, kind of it. And this gives a linear VI, kind of like a Ohm's law. It, not kind of like it, but the Ohm's law. It shows a linear IV characteristics. Sorry, there is no I here. Yeah. Sorry. Okay. Meaning, if you increase voltage, the current also increases, right? If you increase current, no, if you increase voltage, current increases, and it's a linear relationship. So that's really important because the ohmic part or the linear part kind of gives us precise control. But if this was like this, or like this, it would mean that if you apply a voltage, the amount of current that increases, we can't really calculate it. Even if we can, it's really hard to. So we always choose parts of systems which have a linear characteristic, so or ohmic characteristic. Now, this is the most important part regarding a semiconductor that we use regarding all the further applications, and it is the formation of a depletion region. Now I've told you about a p-type and an n-type, right? And p-type has a large number of holes, while an n-type has a large number of electrons. Yeah. So what if we kind of join a p-type and an n-type semiconductor together, right? Now, when this happens, right, we have electrons, holes kind of take in electrons, electrons kind of jump into holes. So this electron, if these are joined together, kind of jumps into this hole and fills the space. And this electron can do the same, this can do the same, and it kind of creates a space, meaning once an electron fills a hole, it kind of creates a negative charge there, right? And once the n-type loses an electron, it kind of has a positive charge. Not kind of, it has a positive charge because the atom is donating an electron and here the atom is taking an electron. So hence the negative and positive charges. Now, this kind of creates a region which has, this is called a recombination of holes and electrons. Now, once this happens, it kind of extends to a certain amount of region. Imagine it's still here. Now, this region doesn't have any electrons or holes, but the holes have accepted it and the electrons, donors have donated it. So this creates a region of positive and negative charged atoms. Now, when charges are separated by space, something called potential develops. And potential develop means there is an electric field here. Now, this potential, we have not connected this device to an external battery source or anything. Now, this is a fixed region depending on the amount of donation we have. So this is called a depletion region. Now, in a PN device, there are two kinds of biasing. Biasing means the direction we apply voltage to. Like for a forward bias, we apply positives to one side and negative to another. If you reverse that, it means a negative and positive. So in a forward bias, what happens is, I told you that develops a potential here, right? The battery, this potential kind of prevents any more electrons or holes to move. But the battery, once you, or a potential source or a power source, kind of reduces this gap and allows more electrons to move from here to here. And these two, there are two types of current caused by this. One is called drift current and other is diffusion current. We'll get to that in later sessions. Now, this curve shows the IV characteristics. Now, when you apply voltage, the current doesn't increase much. Like it increases, but not by an appreciable amount. But after a certain amount, like 0.6 or 0.7, the current kind of jumps out because the voltage kind of breaks this gap between them and kind of pulls out electrons from the atoms and makes them flow. That's, I mean, more as the voltage gets more and more powerful. So that creates a huge amount of current and it kind of sometimes damages your diode. And it's pretty important when you develop devices and think of design and things like that. Now, what is a reverse bias? What if we change the polarity, right? If we attach to the attach negative side and positive side in the opposite configuration, that means the potential V is kind of aiding the resistance developed inside the diode, and it kind of widens this gap, so it prevents any more current to occur, right? So you can see this, the current is kind of flatlining. I mean, even if you increase voltage, there is no current, meaning it's really hard. I mean, there is a region which is similar to that before here too, which means that the diode has broken. I mean, basically it's called a breakdown region. We don't need it here anyway. But now, why do we use transistors, right? Transistors, we can use transistors as amplifiers, but in semiconductors or in chips or in ICs, we use transistors as a switch. So imagine we have a mechanical valve and kind of water is flowing through it. So once we turn the wheel, we can increase the amount of output, right? I mean, get a certain amount of water coming in and a certain amount of water going out. If we open completely, it means a lot of water is coming on completely. But if we close it, no water. But if we keep it in a middle state, the amount of water would be in between those. Now, the same concept is there for an electromechanical switch. It's like if you switch on, it means current passes. And if you switch off, the current doesn't pass. Now, transistor, the switch in the mechanical case can allow none, some, or all currents to pass through it. I mean, water case, but the same thing can happen in electromechanical switch too. Depends on the connection, right? So this is a little tricky part, but I will give you a very basic introduction to this. This will be covered mostly in further sessions because this is an introductory section. Now, in a MOSFET, what we do is, MOSFET's full form is metal oxide semiconductor field effect transistor. I know it's a mouthful, but anyway, field effect transistor is the field is pretty important. It creates an electric field which kind of aids current flow. Now, here we show is an N-channel MOSFET. The N-channel MOSFET, the N-channel, basically you see that there is a blue P region and a red N region, which is plus and plus again. Now, this P region is positively doped region. I mean, it's a donor region, and the N region is an accepted region. The entire block is actually a P region, and you add, in these regions, you add some amount of donors too. So it becomes an N-type semiconductor. And this region is a P-type, and this region is an N-type. Now, the yellow part here, it's a dielectric, or it's an insulator. It kind of prevents leakage, and it also field leakage or dielectric. It kind of keeps so that the system conducts current only in a certain direction. Now, there are two other parts called source and drain and gate too. These are metal electrodes attached to the N, P, and N regions. Now, the source region, we apply voltage. We apply voltage here in this region, and we can apply voltage in this region, and it's all connected to the body here. That's how the diagram would look like. So that's the use of the source, gate, and drain. They are basically used to apply voltages so that we can control the current flow. There is a lot to it, but that's for further sessions. Now, the voltage difference from this gate to the body kind of creates an electric field that opens and closes the flow from drain to source. A phenomenon called carrier inversion takes place, which we would explain later, which kind of is the reason why once the electric field is applied to a certain limit, the N-type and P-type regions are kind of connected and current flows. That's the basic principle of a MOSFET. That's it. I mean, this current flow kind of depends on the voltage we apply. In different configurations, we get different graphs. We'll get into that in a bit. So, and we also need to use the connect it to the body so that it forms a full circuit. Yes. Now, this is basically a childish diagram, but this is the actual diagram which shows the elements and how this form N, P, drain, source, metal oxide, and things like that. Now, the dielectric that we use is silicon dioxide. Because we have silicon, it makes sense to use silicon dioxide because it's, well, from silicon, it's easier to make silicon dioxide anyway. So the voltage kind of determines the current, and the configuration kind of aids the current flow. Yes. Now, this is a little tricky part. This is the 3D structure, and it shows how the MOSFET kind of looks like in a 3-dimensional system. Now, the important part regarding this is the width of it, W, right? It shows here all the semiconductor companies, if you reduce the width, you are basically making a MOSFET small. So all the semiconductor companies in the world are trying to make it smaller and smaller. Once it's small, it means that you can pack more into the device, right? So basically you help increase or sustain the Moore's law for a longer period of time, like for 5 years more maybe. Now, this terminology in COX, TOX and everything, we'll explain later. Now, the channel is the inverted layer of electrons close to the surface is called. Now, this is the region, it's called the channel. That's where the electron flow occurs, and I told you it occurs due to a phenomena called carrier inversion. Now, the potential on the gate electrode forms inversion channel through the vertical electric field. We'll get that, we'll explain the concept and as we get progress further. Now, this is the equation for the current, and this is, yeah, we want to design, the aim for us is to develop faster, smaller, less leaky MOSFETs. So, and for regarding that, we need to reduce W to make it smaller. The length of the transistor is pretty important because every new technology tries to reduce this. When you decrease the width, it means there is a smaller transistor fits into the wafer. Now, mobility, as I told you what mobility is, it kind of shows you how fast an electron can move. And we use fancy materials in and around channel to modulate this. That's really regarding further design. And capacitance, it shows the strength of the gate, meaning how much voltage we can apply without it getting burned up. Then applied gate voltage relative to source, that is kind of related. That kind of determines how the electron flows, or if we can switch it on, switch it off. So again, for another session. Now, these are the current versus voltage diagrams. Now, you don't need to check into all the weird looking curves and the colors and everything. You just need to know 3 words, that is cutoff, saturation, triode, right? In cutoff region, if you apply voltage, you don't get any. It doesn't probably work. It doesn't work. But in saturation region, is the region that we use in MOSFETs. It's the region that's favored by engineers because that's the region we can control and we can use for effective working. But in triode region, it's basically if you change the voltage from source, drain, and gate, you get different kinds of voltage and current relations. And that's the region, but we don't use it much because it's kind of not linear, so we don't kind of need it much. The important region is the saturation region. Now, this is an output regarding VDS and VGS. It's basically voltage from gate to source and voltage from drain to source. That's how the different ways we apply voltage. Now, this shows what happens in a triode region, saturation region, cutoff region regarding current and voltage. You see that in every saturation region, the current is constant, right? It's called saturation current for a certain voltage. Now, that's the entire reason why we kind of favor using the saturation region, because the current is stable. In triode region, it might not be so. It's kind of difficult to control. And in cutoff, there is absolutely no current for a given amount of drain to source voltage. Now, yes, the current flowing through the gate, the current that kind of flows back from here, it's called leak voltage. We don't need that. We don't want that. So we try to reduce it using better materials. Now, cutoff. In cutoff region, these 3 diagrams kind of shows you different kinds of voltage configurations we use to achieve the 3 different states which we need. In cutoff region, the voltage in the gate is below a certain voltage, but drain is positive. Current is 0, because if you don't achieve the threshold voltage, this channel that I mentioned earlier doesn't open up. So basically no current, that's it. And for this part, the triode region, it's kind of same. The current kind of flows, but it's not ideal to use it there, right? Because this is important. Once this happens, the current flows. And because the voltage to drain is kind of small, the current flow is kind of erratic. It's not much. I mean, it's not controllable. And the current do exist, but as I told before, it's not much useful. Then saturation region, that's the region what we are mostly focused on. The important condition that voltage of the gate should be greater than the threshold voltage is it's satisfied. Then the drain voltage is really large, and we get a good current, which is this part, the saturation current, very stable, linear current, and we use it. Now, depending on that, there is change in all these things, how the other configurations and physics of it. We will have other sessions regarding discussing these things. Yes. Now we know that we have a MOS. What if we put an NMOS and a PMOS, right? An NMOS is a MOSFET developed on a N substrate, and a PMOS is one developed on a a donor substrate. So what will happen if we do that? So I hope we can discuss that, and all of you will join us to next section, and we will have a fun section. I hope I didn't make all this too tricky, and if you have any questions, we are really open to have a good Q&A with you guys. Yes, thank you.
Thank you, Kevin.